At elevated temperatures, NO2 undergoes decomposition in the gas phase, forming NO and O2, represented by the following equation. Scientists measure the change in NO2 over the first 100 seconds of the reaction. The scientist uses data collected from the experiment to generate the following two graphs. Okay, so we're looking at kinetics here. I know that because it says explain how the graphs indicate the reaction is second order with respect to NO2. So this is, again, pretty straightforward here. This would be a first order, and 1 over concentration is second. You're always looking for the graph that produces the linear relationship. So in this case, the graphs indicate second order because the graph that's 1 over concentration of NO2 is linear. And the linear graph is the one that indicates what the order is. So again, fairly straightforward with that. Just go through, look for the graph that's linear, and that's going to tell you what the right one is. So at a certain point in the reaction, the rate of disappearance of NO2 is deemed to be 6.52 times 10 to the negative 7th, determine the rate of appearance in this reaction. Okay, so disappearance and appearance, that's a mole ratio thing. So NO2 and O2, so if I go back up here, yeah, everything is in a 2 to 1 ratio. So if I go through and do this, it's 2 to 1 mole ratio of NO2 to O2. So if I do 6.52 times 10 to the negative 7th, and just simply do 2 moles of NO2 and 1 mole of O2, I will get my answer. So take 6.52 times 10 to the negative 7th and divide by 2. So 3.26 times 10 to the negative 7th. And again, make sure proper units, all that good stuff. But yeah, simple mole ratio problem there. Okay. All right. NO2 is a molecule that contains an odd number of electrons. Oh, okay. That is not something I see very often. I can't remember the last time I actually saw something like this on an AP exam. I've only been teaching this for 5 years. But you have an odd number of electrons in this Lewis structure here. So again, not something we see every day. Unpaired electrons presumed to be localized on the nitrogen atom as shown here. Okay, that makes sense in terms of formal charge, I assume. In the box on the right, complete the Lewis dot structure for NO2 plus. Be sure to show all bonding and non-bonding electrons. Okay. So I'm guessing that this is just follow the Lewis dot structure rules to figure this out. So 5 valence electrons plus 12 is 17. We're going to subtract 1 because of the positive charge, so 16 here. So single bond everything. Add lone pair to satisfy your octet rule. Again, I'm following my set of rules here. Your rules may vary. And then what I look at here, so I've got 2, 4, 6, 8, 10, 12, 14, 16. Oh, 18, 19, 20. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Dear God, that took me way too long. 20 electrons in that structure is too many. So we remove a couple lone pair here. And we add a double bond. And I guess we're going to do that to both sides. Sorry. Okay, this is becoming a nightmare. Okay. When we're done. Yes. 2, 4, 6, 8, 10, 12, 14, 16. In terms of formal charge, though, I think that's right. I mean, I can't imagine it triple bonding with anything. I can't imagine any extra lone pair on that nitrogen. You're not just going to take off that lone pair. That leaves some really wacky formal charges. I'm pretty sure that's the right structure. And again, it kind of goes in hand with the next question. I kind of noticed as I kind of cheekily looked at this as I was going through and drawing the dot structure. So it makes claim that bond angles are different from each other. Do you agree or disagree? Based on this, I would agree. For the first one here, this is going to have a bent geometry, and this one's going to have a linear geometry. So again, I'm assuming that's the right structure. That's a bit tricky, in my opinion. But again, if we follow the Lewis dot structure rules, we follow the rules of formal charge, that should indicate the best structure for that. I don't like that formal charge on nitrogen that's here, but I mean, I guess it is what it is. So I'm going to leave it there. I think that's right. I'm going to go with that. So, okay, let's move on. One more and we're done.